Good afternoon. My name is Giles Chamberlin. I'm from the UK, and I'm going to be talking this afternoon about that absolute sacrilegious statement: testing is not enough. There's been some good stuff on testing already. I'm not saying you shouldn't do it, but this story, like all good stories, begins on a Friday just before lunch. A slightly worried sales guy phoned me up. He got a customer meeting that afternoon with a very unhappy customer. He wanted to share the pain. Our software had crashed on their site. They were unhappy. They were an important customer. I was running the engineering group in a startup. So guess what? It was my privilege to get to go along to that. So I spent lunchtime reading through the bug report. We were really lucky. We got some really good engineers who are also very keen on documenting bug reports well. They're beautifully written. So I read through what had been going on. And it was reasonably clear eventually from that. We're a video conferencing software company. If you're not in the video conferencing field, we effectively make a telephone exchange for video systems. If you are in the video field, which a bunch of people at this conference are, as a vast oversimplification, we're a SIP proxy, registrar, and a few other bits, but it's a telephone exchange. And the problem was one of the audio-video guys, technicians at the customer, they'd been using our software for months, no problem, but he'd been trying to make a call from our system in location 1 to a user's video system in location 2. Not unreasonable. And it failed to go through. The reason it had failed to go through was they're a very security-conscious government organisation, and they'd segmented their network, firewalls everywhere. The IP packets they didn't get through. Nothing we can do about it. It was desired not to work, so that's fine. But he didn't realise this. So when the documented way of connecting the call failed, he got creative. And he remembered that back in the pre-standard days, there were lots of different ways of routing a call through one particular directory system to one particular device. And it was all non-standard proprietary stuff. But he tried that to see if we supported it. So you dial the address of the address of the directory, some separator, the telephone number of the system you're trying to call. And he tried a hash as a separator, and an equals sign, and then a colon, and we crashed. Repeatedly. This is why the customer was unhappy. Slides are saturated, slightly bleached out, I'm afraid. But if we look at what he tried to dial, foo.example.com, colon, telephone number. Okay. Let's look at the spec. Let's see what that actually accepts. I've grayed out various pieces which are not terribly relevant, but this is lifted from the RFC. The important bit is the authority matches our input. Host colon port. Host is a host name, colon port. Port is a string of digits. Totally compliant. What are you objecting to? The problem is in the TCP spec, the underlying spec that takes data over IP. And that very clearly defines a port as a 16-bit unsigned integer. That telephone number is bigger than 65,000 and a bit. It doesn't fit. Code low down in our system said, this is not good. Threw an exception where this was mostly written in Python. That travelled up. Nobody quite knew what to do with it on the way, so they passed it all the way through. Got up to the user interface, which was totally unaware of this possible exception, and crashed. And if anyone was at Bjorn's talk yesterday on how to stop a program, we were following a lot of that. We did a snapshot, core dump, log files, debugged the problem in the safety of our own office. Here, there in the log, user trying to call this, bang. So it's nice and easy to diagnose. We had a fix that was going through system tests at the time. So I went into the customer meeting, said, very sorry, Mr. Customer, grovel, grovel, grovel. This was the problem. Can I offer your audio-video technician a job, please? Bug fix coming out next week. They were happy, and in fact, 6 years later, still a major customer of ours. We've had no recurrence of the issue. Great, problem solved. But there's a sort of nasty feeling at the back of your mind, or my mind, after that. Well, it's not happened, but why not? What's going to stop it happening again? It's just not comfortable. So why did we miss it? I propose there's two main reasons, and I'm going to dig into each of these in turn. Testing doesn't scale, and error propagation is lossy. Either you use the whole error, or we lose information in it. It's not reliable. So looking at testing. Software is basically an inverted pyramid. There's an XKCD cartoon I should probably have used here of the entire internet depending on one little piece of software supported by a gentleman in Iceland or whatever. You've got all the user interfaces, user level applications, using the same sort of business logic, using mechanics beneath it to make stuff work, using the OS, using the kernel. And any reasonably designed system, you've got lots of things depending on fewer things, depending on fewer things. Think how many applications run on the Linux kernel. You know, there's a lot of things using a few things. So the software is expanding layers. So the test area keeps expanding. And that means knowledge of what errors could propagate up into that layer keeps expanding until you end up with the frankly ludicrous position of the user interface guy who is organizing dialog box on a web form having to know about the details of the TCP/IP spec. We're a startup, it was probably the same guy. But your whole context has switched, and you're worrying about CSS and phrasing of dialog boxes, not intricacies of TCP specs. So your ability to remember what's an edge condition, what you should be testing for, reduces. Now, there's various approaches to testing which can improve that. But I think the fundamental problem is you're getting an ever-expanding surface to look at. So even if we assume the software underneath is bug-free and it's just reporting errors up to you, you're getting more and more conditions that you've got to handle. What can we do about it? One idea is to embed the tests in the software itself. Rather than having separate unit tests, you have the tests embedded in the software as contracts. This was first, to my knowledge, formalized by Bertrand Meyer back in 1985 in his Eiffel language and publicized in his book, Object-Oriented Software Construction, which is a beast of a book. It's about that thick. If anyone else has ever read it, the typography in it is abhorrent, but it's got some interesting ideas for something 40 years old. He was also proposing object-oriented software construction, which was radical. And there was an idea about reuse in there as well. One of the nicest things about this, as well as formalizing the preconditions on a function, what you're prepared to accept, is the nature of the program, the nature of the Eiffel language is to use automatically generated docs from the code. Again, this was back in 1985, not bad. And those preconditions, postconditions, are extracted into the documentation. So at least you're now formally taking this domain knowledge, this limitation on the function, up a layer. So if your user reads the docs, okay, big assumption, if the user reads the docs, they've got a chance of knowing what's going on. This has been a popular idea in theory for a while. Closure's picked it up. C++ has been trying to pick it up. It didn't make it into the standard in 2020. It might next time round. But lots of interest in trying to get it into different languages. Interesting side effects when you start having functions as first-class objects and passing them around, but that's for another time. The problem comes, what do you do when these contracts are broken? Because like the unit tests, it's basically an assert. It's only exercised at runtime, and you've got to throw an exception or some means of signaling an error up, which you either make a no-op at runtime in production code. My personal opinion, that's a very bad idea. Or you rely on the higher layers handling it. That's what got us into this mess. So, okay, the formalization and the embedding is quite nice. The runtime stuff, less so. The other stream we were going to look at was the error propagation. We've got two main ways of propagating errors. Either an error code returned in band, so typically some sort of sentinel value that says, if you get this back, if you get -1 back, then something went wrong. And you might send an error code which defines what that something was. Or you throw an exception and that propagates through. Error codes, very, very easy just to not check. Everyone here always check printf error codes? So it's very easy to lose them. And even if you don't, you've got an error code back from a lower layer. You can't handle it. What do? Well, if you can't handle it, you've got to pass it on. You've now got all the error codes from this function, all the error codes from that function. How do you pass them up? Oh, I know, I'll squash them all into a single error code for me. I went wrong. You're losing information. By the time it gets up to the top layer, our poor little user interface layer again, the world went bad. Nothing you can do about it. And exceptions, okay, it saves you the problem of having to mash them all in together. You just ignore them, and the problem goes away. All the way until the top layer where it goes bang. Usual approach, and the one we're taken, is you just have something at the top layer that says, if unexpected error, whoops, crash the system, grab everything you can, and apologise. Prepare for a Friday lunchtime meeting. Simplifying the problem, square root. Highly sophisticated implementation of a C-like square root. If the number's less than 0, return not a number. Otherwise, off you go, have fun with Newton's method or whatever. Great. That nan is interesting. It's implementation dependent. It basically typically uses the floating point hardware to pass magic around. And the effect of it is hardware guys will shout at me, comparable to throwing an exception, just saying something went wrong, and you then call a special function, isNan, to see what that thing was. Same problem as checking the error on printf. You know, in routine code, how often do you call isNan? And even if you do get that problem back and you do call the code, what do you do with it? So we've got the hassle of invoking this. It's difficult. Let's take a different approach. Let's make it impossible to have that bug. We're going to try and make impossible states, so something that would cause that isNan, square root of -1, to be impossible to occur. Now, skipping minor problems about machine representation, performance, history, little things like that, let's change the signature of square root. If we invent an unsigned double, comparable to an unsigned int, and have square root take an unsigned double and return an unsigned double, you can't give it a negative number. Nasties about integer overflow and so forth aside. If you can't give it a negative number, it can take the square root of any number you give it. All of that error handling goes out the window. And this comes under the heading of the difference between total functions and partial functions. Anyone remember that from? No? Okay. Total function, basically any input you give it, it can give you a valid output. So if you have a function which takes any unsigned double, give it any input, it can give you a valid output. A partial function, that's only partially true. Some values of possible input provide an invalid output. So square root taking double, pass it -1, bang, not valid. And we can see that total functions suddenly massively simplified the world. There's a valid output for all possible inputs. We don't have to handle any errors. That's attractive. Go back to our original problem. Okay, well, port can only be 0 to 216. 2 to the 16. Make it a D word. Matches the spec. Yep, that do. And a lot of languages do. But that's a bit of a special case for this happens to have a spec that says 2 to the 16. What if perversely the spec said 2 to the 14? Okay, there's no native type to fit that. There's also other port values we might want to exclude. If you go back to the IETF spec, there's a whole series of reserved ports for future use or experimental use, which if you're being well behaved, you should be excluding. And for your own sanity, and depending on what you're doing, you probably want to exclude port 0. So we'd like to make it more flexible, more general. So looking back at our problems to date, preconditions, tests, assert, only fire at runtime. And we've got to do some error, ideally, we've got to do some error handling to handle them at that runtime if they do fire. And that's what got us into this mess in the first place. We'd like them to move them to compile time, make the world saner. We'd like to make impossible states impossible to represent. And this comes back to the difference between total functions, can't fail, and partial functions, which can. And the example we went through was the complexity of having to assert for a positive value in square root, as opposed to the simplicity of just saying, I'll only take in positive values, and skipping that entire test. Classic software engineering solution to everything, shove another layer of abstraction in. Now there's going to be various performance arguments that people could raise at various points. Yes, if you can measure performance and prove it's a problem and that this improves it, knock yourself out. Otherwise, I propose a layer of abstraction as opposed to grovelling at a Friday meeting is a great improvement. And the idea of wrapping it in this type is that the low-level types say, give me a port. I won't accept anything other than a port. If you give me an integer, I'll fail at compile time and say, what are you doing, you idiot? Give me a port. Any intermediate layers know they've got a hand on a port, so they hand on the port. They've got to have something they can hand on. They don't know how to make a port, so they're going to require a port as well. So this dependency is going to go up the chain. Each of them will naturally require a port as its input. And eventually, this is going to bubble up to some layer of software which can make a decision. In our case, it was the user interface, where you've got a string representation of something coming from a dialog box on a web form, and I want to convert that into a port. At that point, I can use a factory method and attempt to convert this string into a port. At that level, I need to know how to convert a string to a port and what's valid, because I've got one and I've been asked for a port. Okay. And I've also got the advantage that if it fails, if I give it an invalid string for the port, I'm at a point where I can do something about it. I can either say invalid config file, or put up an error on the dialog box saying, sorry, that's not a valid port number. If I want to know details of what's valid, I know where to find out the documentation with the factory method, because that's the one that's rejecting it. So we've got a factory method that's going to be given something and is going to return a port in this case, or a wrapped thing of value. We don't want to raise the whole error propagation thing again. If we throw exceptions, we've got all the problems of people not handling them, them wandering through, bang. And it's also tempting to maybe push the problem down a bit. Oh, I'll give you the string, you sort out converting it. Because it's very easy, if you're running up against a deadline, say, oh, it'll be all right. I'll change it later. I've done that. So we don't want to use sentinel values. We don't want to use exceptions. We want to make it really obvious that the method can fail. So there's a big flag going off in the developer's mind at the time of invoking it that says, oh, look, this is a binary choice. It will either work or it won't. The case of it doesn't work isn't, oh, that's really unusual. I wasn't expecting that. No, it's signposted, big letters. This can fail. You've got to handle that. Now, fortunately, there's a nice type already in existence. Optional, it's called, in C++ and Java. Maybe in Haskell. I'm going to use a couple of Haskell examples, not going into any Haskell code, but it's quite an interesting place to play from. Anyone use optional fairly regularly? Good. Okay, so the next couple of slides are easy, about half. Again, I mentioned date of signed by contract. Haskell got maybe in 1996, Java in 2014, C++ in 2017. So yeah, been around 7 or 8 years in the standard, and we've got reasonable take-up. Just for those not used to it, as a client of it, I've faded out the boring code in here. Key stuff's within the conditional if. So we're going to call some sort of factory method string to int. That's going to give us back an optional int. So it either contains an int or it doesn't. And this is as distinguished from the classic null pointer type thing where null pointer might be a valid result or 0 might be a valid result. So there's a totally separate thing which is either good or bad. We test the optional itself to see if it's got a decent value in it. If it has, we use that value. If it hasn't, we handle that omission. The string we've been given isn't a valid int. What is my behavior to deal with that? Haskell version of this maybe returns either nothing or just and then the wrapped thing, just an int in this case. And it uses pattern matching to extract it, so the code's slightly shorter, and more to the point, the compiler can check the pattern match to see if you've forgotten to put in the second branch. If you haven't put in a match for nothing, it will complain to you. Neither the Haskell version nor the C++ version prevent you shooting yourself in your foot. It means when you shoot yourself in the foot, you should have a bad conscience. You should have a bad feeling when you're taking an optional and saying, neglect the possibility it could go wrong. Haskell version of ignoring the second branch, there is a just function which says, I know you're an optional, just give me the value. Oh, you haven't got one? Crash. The docs flag it. If you put in your code, you feel so bad. But it's there if you need it. On the other side of this, moved away from C. I used to write a lot of C++. I realised with horror I haven't since about 2000. So I decided I wasn't going to write any. But basic form of the factory method, you pass in some value, you make some decision on that value. If that decision is valid, you return a wrapped value. Otherwise, you return whatever your sign is for failed. Simple, effective. A couple of bits. You now need access to this make foo method from high-level code, whereas before I was just passing in an integer. I've now got to find out a way of making a foo up at the high level. Yep, but that's just formalizing a dependency you already had. But the dependency you had before, sorry, yes?
So we have a make foo function which does not mention foo at all. Is this intentional?
No, it is bad slide. Yeah, I apologise totally. It was a late night slide. It's my factory method to make whatever the thing is I'm trying to return. The fact you need access to this method down at a low level, down at the high level, is replacing the fact you used to previously have implicit domain knowledge of the restrictions on that method. What were valid integers to pass into the make port function or whatever. You've now got those explicitly called out. Code's duplicated. If you've got lots of these little factory methods around, you've got lots of the same thing. If some predicate on some value, return wrapped value, otherwise fail. Okay, it's not exactly mind-bogglingly complicated code to duplicate, but yeah, it's ugly. And again, slightly less critical, but if I've got a value I'm passing in that's hard-coded, and probably shame on you for hard-coding values, but there might be good reason. At runtime, I've got to go through this if-else branch, and I've got to performance it. Okay, we'll skip that for now. We'll come back to that briefly. It's not really a critical problem in most cases, but it doesn't feel good. Code duplication, on the other hand, that's easy. We can factor that out into something that takes a template, takes a value type, and returns a wrapped value type. That exists. A couple of examples: strong types in C++, and Haskell in its refined library. Very, very easy to do. And I've been singing the praise of Haskell a couple of times in here. And when I started coming up with this talk, I thought, yeah, let's go back and see how well they do this. So I searched for port through something called Hackage, which is the Haskell package archive. It's not something like the standard library. It's lots of contributors, so varying quality, shall we say. There are quite a few implementations. The main, one of the most popular web servers, had a very nice implementation which wrapped a D word. It didn't use a factory method, so I prefer one with a factory method, but yeah, it's good. Despite my singing its praises, the vast majority of them used int, which is basically the same as in 32 on most architectures. So yep, wrong, bug. My favourite didn't. It used a type called integer, which has got quite expensive runtime performance, but has a great advantage of allowing you to scale to infinitely sized integers. So they've gone out of their way to work with even more error-prone values. So yeah, that was good. But hey, it's good in theory. So that's been quite interesting. That all exists in code today. Standard libraries, common libraries, and it's mostly a mined approach. And again, the Haskell guys have coined a phrase for it, which is paths don't validate. So effectively convert types, parse it into a new type, rather than validating, doing this if else at every use point. And it works quite nicely. And the localization of the error handling. You only have the error in the area where you've invoked the problem, rather than way down and possibly much later, asynchronously. Makes life so much easier. We're now going to move a little bit more esoteric. So this goes slightly beyond what you can probably go and do in your code base tomorrow. That irritating runtime overhead we mentioned. Was anybody in the real-time safety talk with Anders on yesterday morning? There's a couple of comments in there on the compiler analysing the code to prove whether various conditions are true. This comes through also in the type system, and how much this comes through depends on how formal your type system is. And this is where some of the languages like Haskell have a formal computer science basis to their type system. Others have a more pragmatic one. And then still others, Python, where we had our problem initially. We were initially working in Python 2.7 for most of our code base. The time critical stuff was in C, but a lot of the surrounding scaffold was Python. Python 2.7 didn't have any type system. Python 3 subsequently has a bolt-on type hint system, which we are using quite extensively now, which is an interesting step in itself. But anyway, it's leaving off on a tangent. The compiler can perform type analysis on values that are being passed into it. And so in that case, if you've got a hard-coded value you're passing into this refined type, it can detect errors at compile time. And depending how far through, how complicated the relationship between your original value and where you're trying to prove its type, you can make more or less assumptions. So as I say, this is called refined types in type theory. There's actually a subset of this I first came across in the 80s, but it's been in Pascal since 1970, which is integer subranges. So it's a very, very limited case of this. But it's just what it says. You can have a subrange of integers. So, I will allow any value, I will accept any value between 0 and 99, useful for number of cents in a dollar or whatever. And it can do real-time, it can do compile time type checking for very simple relationships. And it can also do real-time checking, where it will throw an exception on detection of an error. Well, that's a theory. Most Pascal compilers turn it off by default and nobody ever turns it on. So you carefully put all this safety features in your code base and it never gets turned on. Yeah, okay. But that's personal mag. And then here we move from the, okay, that's interesting, refined types, there's bits of that in Haskell, yep, and various other languages. Now let's go to the here be dragons bit. Refined types are just a subset of dependent types. Oh, before we dive into that, one other little point for the couple who are in the risk software thing. Runtime safety. The whole idea of marking stuff as blocking and then analyzing back through that so you could trace where all these dependencies were going. Again, interesting reflections in some of the functional languages. If you look at the I/O monad in Haskell, that's carefully taking all I/O out into a separate subsystem, not for reasons of efficiency, but because you can't make the same statements about no side effects in I/O code. It is going to have a side effect. It's its whole point. And once you start having side effects, you can't do things like reordering statements arbitrarily. Printing lines in a different order tends to irritate people. So the I/O monad is a interesting contrast with things like the blocking is quite fun. Anyway, if you want to move on into Dragonland, there's a whole world of dependent types. And I haven't delved into this very far yet. It's a series of rabbit holes and you go deeper and deeper. But so far, the refined types are strong types. They were basically constraining a value by a predicate on it. So pass a value, compare it with a simple predicate. Either this is or isn't an even number or whatever your predicate is going to be. Dependent types take that much bigger, not a predicate on a single value, but they can take it on a whole context around. The nature of that gets horribly complicated, but for a very simple example, imagine you've written a function to flatten a matrix. So it takes in a matrix of dimensions x by y, and it gives you a vector of length x times y. The dependent type system can say, okay, I know that the length of that vector will always be x times y at compile time, if I can prove the dimensions of the input matrix. In that case, I can pass that on as the type of the thing I'm passing on to the next function. And if the next function requires an even length matrix, because it's going to split into two, then you can prove at compile time that a 3 by 3 matrix is unsuitable to be passed through, and that will fail much earlier in the system at compile time. I'll keep harking on about this. The earlier it goes bang, the better. And then you get into the next stage, which is just weird and keeps the computer scientists really, really happy. And long may they stay quietly happy in their corner. The whole world of proof assistants, which are taking this to the next level and proving that a program is correct. Bunch of examples: Agda, Idris, Koch. It's a world unto itself. But run away at that point. And we'll look at where we got to. It's too easy to rely on primitive types. Our problem at the beginning was caused because we were relying on a primitive Python type, an integer just being passed through. Bang. If you want to have a Google, there's all sorts of rants on primitive obsession. And another one I hadn't come across till recently, Boolean blindness, which is quite a nice little idea. I've been very guilty often of putting a little Boolean flag on my function, whether or not to invoke this other behavior. Am I the only sinner? Okay, probably. Which is great, until you're reading the client code, the person trying to use your function, and you're reading it probably 3 months after you wrote the original one. There's a flag there that says false. Okay, and you've got to go away and look it up and find out what false is. If you just use a two-valued enum, you get exactly the same behavior, but you've got a sensibly enabled value. Oh yeah, and when a third state magically arises, it's dead easy. So have a think about, is Boolean actually the thing you want always? But anyway, enough of that. All the way through this, the tighter you constrain things, the better. You've got to test for fewer things. They can't happen. If they can't happen, that's a good thing. So you're making impossible states impossible to represent. And the earlier you can do that, the better. Which brings us back to that spec mismatch. That's where all the pain came from. And the problem is, the SIP spec uses a different schema from the TCP spec. IETF specs used to be very, very dry and terse, with either bit-based annotation or BNF notation, and it was all highly technically specified. And there's a decision made to try and make them more readable. They moved to this sort of open text of the SIP RFC. But the schema there cannot represent the constraints of the TCP/IP spec. There's no way within the schema they have to do that. So they can't match. Which is interesting if you look at AI code generation. Now I'm going to contend that natural language is a looser spec than just about any computer language. And I even include PHP in that. So if you can't give an AI a tight spec, even ignoring hallucinations and minor issues like that, if you can't give it a tight spec, it's going to be quite difficult to get tight code out of it. Which is an interesting thought. I'm not sure if that's a happy thought or a bad thought. But enough on that. I'm going to try and end this as I did start, with a personal story. And I'll try and keep it together a bit here. But I have to. My mother-in-law, who was a very, very good ceramic artist, died earlier this year. And the morning of her funeral, I went into her workshop just to be quiet for a bit. And it's a fantastic place to be, incredibly creative place. And stuck on the wall, amongst various other things, was this. To be static and satisfied with one single solution does not allow the possibility of development, exploration, and discovery. Bringing that back to software, I've shown a couple of places, quite a few places through this, where some of the ideas I've been taking have been taken from what's fair to call niche programming languages at an early date. Eiffel, 1985, designed by contract, and then brought in to mainstream languages a bit later. Contract, C++, 2025 plus. But it's moving that way. So go and explore some niches. Go and try some silly languages, areas you haven't tried. You may get some ideas. You may come back saying, that is absolutely stupid, it will never work. Okay, you've learned something. And most importantly, you might have fun. With that, over to you. Anyone got any questions? Or just in dire need of coffee? Yes, certainly.
Yeah, so you were using Python and the kind of bolt-on typing system. So are you then, since you're not actually getting any runtime validation, are you then using some kind of type linting thing to kind of get you there?
Sorry, we were using Python for the...
Yeah, you were talking about you using Python in your zip software, right?
Yeah.
Yeah. So, and you said you used bolt-on type system, right? Type hinting system in Python.
Yeah.
Yeah. So, apart from kind of getting some help in your editor with kind of IntelliSense, do you then use some kind of type linting system?
Yeah. So, yes. The question is, how do we implement types in our Python software now, apart from getting smart hints in our editor? First off, I use Emacs, so smart hints are probably out the window. There is a whole ecosystem of software in Python that is basically a linter for enforcing types through there. So it can be programmatically verified and is in part of our CI system. So it's a semi-detached type system, not as good as having it bound in, but we chose Python for the implementation initially because we were a startup. We needed to make progress and money quickly. In a previous life, we'd experimented. We'd tried writing a project in Erlang. We'd run away from that, screaming. We'd tried writing another one in Conductor in Python, and that had worked out surprisingly well, keeping the performance critical stuff in C, C++. So we had some experience, and we thought we'd take the chance on quick money over the more handcrafted approach. Overall, worked out very well. Porting from the 2.7 to the 3 family was painful in the extreme. And we're now starting to experience some of the limits of it, having to retrofit types and so forth, type hints. But yeah, it's been a good experience. I've moved away from the coalface on that, I will confess. So that's a problem for others to solve. Yes.
Point of contention.
All good.
You mentioned that the user interfacing code does not need to consider the RFC standard, which I think I would disagree with very well, because the input sanitation could have caught this problem. The user is taking a port number that is wider than the field available.
So the question was, it was
Point of contention.
yeah, point of contention was it was being asserted over here that the user interface does need to worry about the RFC standard because input sanitation had failed in the user interface, and that was where all the problem came from.
It's not wrong to handle it further down as well.
No, I would contend it is wrong to handle it further down. I agree wholeheartedly. I don't think the user interface should worry about the RFC, because the poor UI designer probably does not read RFCs. But what he needs is to be given an absolutely clear, you've got to call this function, which might fail. Here's the documentation of that function. And if it fails, you go back and ask for a new value. So my factory method at that level. If you handle the problem further down, you're lying because you don't know how to handle it. Sorry, I explained myself badly, and thank you very much for clarifying.
No problem. Good clarification. I agree with your point that you can actually document it and help each other by doing good communication between if we're going to use the front end and back end models.
Yeah. And particularly as the person you're helping, 9 times out of 10 is future you. Coffee. Oh, sorry, one more question. I'm sorry, I have slightly bad hearing. Can you come up a little bit so I can hear you?
So in one of your slides, you say making it impossible to represent erroneous states. And typically in C++, that means defining strong types and adding some constraints to those. But then you also get to the problem of too many strong types and defining all their interactions, and the complexity very quickly explodes. Where do you draw the line? Are there any?
I think it's to segment the creation of this strong type as far away as close as possible to the place where you can make a decision about it, away from the place where you might be using the strong type, where you can't make decisions about how to create it, rather than trying to propagate that problem all the way through a linear chain. Perhaps we can take that up afterwards and follow through that. Last one.
Yeah, can we take this up? Because I don't actually understand the problem. So what, if we have time?
Yep, absolutely.
So what's the problem with having too many strong types?
Well, I don't know. In the industry that I work, usually in finance, so let's say I define a type for price or quantity, and there's so many different types in finance, and then now all of them have different interactions, right?
What do you mean interactions?
Well, how do you, there's this strong type, there's addition, subtraction, multiplication, and now it becomes a computation problem, right? That you have to define each and every interaction. And typically, it's very easy to define strong type, right? We just add a tag to a struct and then it becomes a strong type. But people don't bother defining all these possible interactions with all the other types in the system so far.
Okay, we could have great fun with this. There's going to be a bunch of people in here who are very bored, and we've got a guy on the audio who needs to step out. Can the three of us and anyone else who wants to play grab a drink and chat about it? And thank you very much, everybody.